Okay, good day. This is Math 140 College Algebra. I'm Professor McCulley. This is lesson 6-4, application of exponential functions. Let's talk about it. Today we're going to apply exponential functions. We're going to use the graph of exponential functions, and we're going to apply the continuous growth function. Let's see what those look like. And so here are some exponential functions of importance. This thing is your general exponential function. Here is the simple interest formula. This one right here is the compound and this one is the continuous, C-O-N-T-I-N-U-O-U-S, continuous growth formula. And I call this the PERT equation, A equals PE to the RT, PERT. And in all instances, P is the principal or the initial amount. R is the rate as a decimal for a percentage. So just if you are given, let's do a better job. If given R equal, or let's not use R, G-I-V-E-N, 10%, then R equals 0.1. So you got to change that to a decimal. N is the number of compounds. So if they say it's compounded monthly, your N will be 12. If it's compounded daily, your N will be 365. And T is the time unit. Usually that is in years, but that's not always the case. All right, so some growth versus decay. If this is our general formula and A is the initial amount, then in general, an exponential growth equation, A, B, and X are all positive values, and B is greater than 1. So if all of that is true, then you can say that we'll have a growth formula. Decay, though, there's a lot of ways to look at it and get decay. X could be negative. If X were negative, we could possibly have exponential decay. And if B were between 0 and 1, we could also have exponential decay. Now, even though those are two vastly different looking things, they are related in the fact that we know that a to the negative x is equal to 1 over a to the positive x. And we can write a negative exponent and possibly have a fraction. And I suppose I should also say that 1 over a to the positive x could be written as 1 over a all to the x, because 1 to the x power is just always going to be 1. And so since these two things are true, both of these are going to give us instances of decay. So let's take a look at a couple of equations here. We have f of x equals 3 times a half to the x. We have f of x equals a half times 3 to the x. And we have f of x equals 4 times 3 to the negative x. If I grab my graphing calculator and I clear out all of the stuff that I have here, if I go 3 times 1/2 raised to the x, and then if I go 0.5 times 3 raised to the x, oops, I don't want to put that there, let's put it down here, and then the last one was 4 times 3 raised to the negative x, and let's go and zoom that on a standard window. Here I can clearly see that the red function is exponential growth, the blue function is exponential decay, the black function is exponential decay. And so if I look at my graph, what's in common? Here is an instance where I have my b, that is a fraction between 0 and 1, and here is an instance where I have a negative exponent. And so these two are going to represent exponential decay, but I could also rewrite f of x as 3, oops, let's get my proper tool here, as 3 times 2 to the negative x, and I could rewrite this one as f of x equals 4 times 1 over 3 to the positive x. So again, you can see how they're related based on the fact that negative exponent is 1 over a positive value. All right, let's answer some questions here. It says complete the table to determine the end balance A for $5,000 invested at 12% for 10 years, compounded n times year. So right off the bat, we see compounded. So immediately when we see compounded, we're going to think A equals P times 1 plus R over N, and again, R and N there, all to the NT. And then we'll make a table of what we know. So it says we're finding A, so A is an unknown. We're going to fill in the blanks there. P is the initial amount. That's what we started with, so 5,000 there for our initial amount. Our value for R is 12%, so we're going to put it into our calculator as 0.12, and then our time is 10 years. Now, if you notice, there's only two variables. There's N and A that we don't have values for. We're going to be plugging in N, and we're going to be calculating A, so that's kind of a plug and chug there. We can go in our graphing calculator, clear out all of this stuff, go back up to the top, hit 5,000, and then go 1 plus, oops, let's go 1 plus 0.12 divided by x, all raised to the x times 10. So our number of compounds n times 10 years. And since the difference in the numbers here between values is not consistent, all right, it goes up by 1, it goes up by 2, it goes up by 8, it goes up by a bunch. Since it's not the same difference, we want to make sure that when we hit our table, we are on ask so that we can enter a bunch of different values. And here we go. So for 1, 2, 4, 12, and 365, we're going to enter this set of data. So let's put that in, and remember it's dollars. So it's 15. Let's see, 15,529. And I would assume that there's some cents here, but the graphing calculator only goes to 5 places, so we're going to have to just live with that. 16,063. Sorry, I've got a phone call. I meant for that to be turned off. Sorry about that. I'll call that person back later here. Where was I? 16,036. Put some dollars there. The next one, 16,310. The next one after that, 16,502. And the last one, 16,597. And these are all dollars. And again, there's probably some change, but we don't have that, so we'll move on. And for continuous growth, anytime you see continuous, you should be thinking that PERT equation, A equals PE to the RT. And for us, we will just type that into our graphing calculator. We'll quit out of this. We'll clear this out. And it was 5,000 second. Hit the LN button to get the E. And then it was 0.12 times 10 for 10 years. And we get 16,658 cents. 16,658. Now here's the crazy thing. Notice that even over 10 years, Compounding one time a year to continuously forever, every instant at every moment, only increases the amount that we've gained over 10 years by $1,100. So compounding more than 365 really doesn't actually give you a ton of change. All right. Maculainium is a radioactive element with a half-life of 250 years. The half-life function that models a certain sample of maculainium after 15 years is given as Q equal to 15 times a half to the T over 250. And just for the sake of argument, let's say that Q is measured in grams. I didn't write that in there, but I do want to do that. So determine the initial quantity. If I think of this as y equals AB to the x, like we did for general, A is usually that initial quantity. So in this case, A is 15 grams, because that's what Q is measuring. And then determine the quantity after 700 years, so B. Notice that the half-life is 250 years, so 250 twice is 500. 250 three times would be 750. So if we're going 700 years, we're almost doing 3 half-lives. So half of 15 is 7.5, and then half of 7.5 is like 3 point something. So we should our guesstimate is going to be somewhere around 3 point something. So if I grab my graphing calculator and go 15 times a half raised to the 700 divided by 250, I get 2 point, so almost our three half-life, our third half-life there, which is pretty close. So 2 point, what did I say? 2.154 grams. Well, what we have? 2.154 grams. All right. And you don't put GR McCully, it's just G boxes. There we go. All right. The population of Maculatopia, the perfect planetary society, and with a name like Maculatopia, how could you go wrong? Can be modeled with the following function, where P is the population in millions and T is the time in standard years. So what is the initial population at T equals 0? So again, if I'm looking at it as y equals a b to the x, that a, that's my initial value. But it's not 53.2 because remember, P is the population in millions. So this is 53.2 million people. And B, what is the population after 20 years? Well, we would plug in a T equaling to 20. That is going to yield us, so if I go 53.2, what did I say it was? 53.2 E, so second E, 0.094 times 20 for 20 years, we'll have 348.646. So 348.646. And again, P is in millions of people, so we'll have to do that again. Which is a huge expansion of people. You go from only 53 million people to 200 or 348 million people. They're either really resilient or they're having lots of babies. And it says, when will the population equal 100 million people? Well, if I set up the equation 100 equals 53.2 e to the 0.9 094. Did I calculate that wrong? I had 094. Okay, we're good. I thought I had made a mistake. 0.094 t. All I'd have to do is solve for t. Now we can do that. You can divide both sides by 53.2, take the ln of both sides and solve that. But since we've got our graphing calculator and we've already got some of this stuff done, Here's what I suggest we do. We can go to our y equals, clear this stuff out, go 53.2, go second e to the 0.094x, and then in that second column, let's go 100, and then change the window so the y values is over 100, because if you don't have it over 100, we're never going to see the intersection. So I'm going to go 110, and we'll go by, say, 20s, and then we'll go second graph. Oh, I don't want to go just regular graph. And here we clearly see that intersection. So if I go second, I hit that trace button, go 5 for an intersect, and we just want to get close. So I hit my, oh, that's good enough. Hit enter 3 times, and at 6.714, t equals 6.714, and it says, when will the population be 100 million people? So 6.714 years from now. And that is our answer. Well, that's all I got. So the Marvel fun fact of the day, Ant-Man and the Wasp 2018. Lawrence Fishburne plays the character Bill Foster. Michael Douglas, who plays Hank Pym, is also in Ant-Man and the Wasp, but he played a character by the same name of Bill Foster in the movie Falling Down from 1993, which is a very different movie, as evidenced by Mr. Douglas carrying an Uzi. Both movies are excellent in my opinion, but they are very different characters. That's all I got for today, folks. Have a good day. Bye.